So in the previous segment we looked at two important things. One, we studied stimulated emission in detail from a subatomic perspective, that is from the point of view of electrons and energy levels and the shift of electrons between energy levels. What exactly is stimulated emission, what happens in stimulated emission, and how that leads to laser light production. And secondly, under what conditions stimulated emission dominates over the other two processes, which are stimulated absorption and spontaneous emission, and how that dominance leads to laser light formation, and what are the conditions necessary for that dominance. So under those conditions, one of the things we learned was that a higher energy level should have more electrons than a lower energy level, which is not the case usually, so which is achieved by something called population inversion. So these were some of the things we looked at. So in this segment we will be studying population inversion in a little more detail, and we will also be trying to understand how exactly the stimulated emission happens in a laser setup, which consists of your active medium, your pumping mechanism, and those two mirrors, the reflector part. So this is your entire setup for a laser. These are your two mirrors. This is the space where repeated amplification will take place. This entire space is made up of the active medium's material. So whatever material you are going to use as your active medium, from which electrons are going to undergo stimulated emission, that material occupies the space between your two reflectors, and underneath you set up the pump, which is going to be the pumping mechanism. So this is what we have initially. So once the pump is switched on, electrons of the active medium are excited to the upper state. So what does the pumping mechanism or the pump do? To quickly recap, it takes electrons from the lower energy levels and starts populating the higher energy levels with these electrons. And that is necessary to fulfill one of the conditions required to make stimulated emission dominate over the other two processes. So once the pump is switched on, this process starts happening. That is, electrons from the lower level start going to the higher upper level. Initially, a spontaneously emitted photon triggers stimulated emission. So these electrons which are going to the upper level, one or two of them initially undergo spontaneous emission and come back to the lower level. Spontaneous emission is when the electron comes from a higher level to a lower level on its own without any energy being provided to it, usually because the upper level is too unstable for it to handle. So what have we seen so far? The electrons go up to the higher level, and then one or two of them come down spontaneously, giving out photons, of course. And these photons trigger stimulated emission, because as we already saw yesterday, all that you need to trigger stimulated emission is some sort of incident energy, some sort of photon, right? So the photons which are given out because of spontaneous emission, they themselves trigger stimulated emission. How? These stimulated, so first of all, you get one or two spontaneously emitted photons here, which travel across the resonator in random directions, random phase, and the electrons which are now in your upper level, they are triggered by those photons to release more photons themselves. So they also start releasing photons and coming back. So that is stimulated emission. Now these stimulated photons travel axially through the excited medium. Axially means more or less horizontally along the axis, in turn triggering more and more stimulated photons, thereby undergoing amplification. So first there were a few spontaneously emitted photons. They triggered stimulated emission of some photons. So now these photons are going to, the ones that came out because of stimulated emission, as we know, they will travel in a particular direction, in uniform direction with uniform phase and so on, right? So they travel axially, that is horizontally. So this you can approximate as the spontaneously emitted photons. Here most of them are traveling in a sort of uniform direction along the axis. They are the stimulated emission triggered photons. So now these photons again trigger further stimulated emission. So looking at these, more electrons will be encouraged to give out photons, and the process repeats. So they keep moving axially and they trigger more and more simulated photons, thereby undergoing amplification. These axially traveling photons undergo further amplification for each pass through the resonator, and the mirrors at the end of resonator reflect back the photons. This is what we studied under repeated amplification. So as they are moving axially, every time they hit a mirror, they are reflected back, and for each pass through the resonator, they undergo further amplification. What does this statement here mean? For each pass through the resonator, meaning each complete trip from left to right and back to left, or vice versa, while they are on the trip, they are going to trigger more simulated emission. So they are joined by more photons, meaning they undergo amplification. So it is important to note that while this axial movement and repeated amplification are happening, some amount of spontaneous emission is also happening. It is not like we had some spontaneous emission at the very beginning and then it triggered stimulated emission and then spontaneous emission became zero. That's not how it works. So spontaneous emission is also happening side by side. Meanwhile, the electrons which are inside the setup, they trigger more stimulated emission, and the pump is also running all this while, so you're also getting more electrons from the lower level going into the higher level, which is absorption. So everything is happening concurrently. Now, stable laser emission is initiated when the gain per pass through the resonator becomes equal to the loss per pass. What does this mean? So before we go at stable laser emission, let's see what gain per pass and loss per pass are. So one pass through the resonator, as I said, is a full circle trip the photon makes from left to right and back to left, or vice versa. So during that one round trip, some spontaneously emitted photons are also going to enter the resonator setup, and because they are going to be incident at random angles, for example, you look at this particular photon here, it is likely that some of them might be lost. Some of them are incident outside the setup at angles which go outside the setup, and these are lost. So that is the loss per pass, the number of photons lost when the stimulated photons are performing one complete trip through the resonator. And usually the photons which are lost are ones that are spontaneously emitted, usually, not necessarily always. Secondly, gain per pass, like I said, is even as these stimulated photons are traveling axially, they are going to trigger more stimulated emission, more photons are going to join them. So those are the gain. So we can say that stable emission is happening when the gain and loss balance each other. So effectively, at least whatever is inside, because you are gaining at least as much as you lost. If the gain is greater than the loss, well and good, that's going to be great, but if not, at least the gain should be equal to the loss. So when the gain per pass equals the loss per pass, we say you get a stable light. So the minimum population inversion that needs to be maintained so that gain is equal to loss is called the threshold population inversion. So why is population inversion important for maintaining stable emission? As in, we know why population inversion is necessary to achieve laser action, because it fulfills one of the conditions, N2 should be greater than N1, that we are aware. But for stable laser light emission, why is population inversion important? Because spontaneous emission is, as the name suggests, spontaneous. It is not something quite in your control. So the loss per pass totally depends on spontaneous emission, and that is not something that can be controlled from external interference in any way. So the gain, however, depends on a lot of factors, one of them being the population in the upper level. So if you want to make the gain equal to loss, or gain greater than equal to loss, because that is when stable emission is achieved, you cannot change the loss. You can only make sure the gain is more. How do you make sure the gain is more? By increasing the population in the upper level. Because that is one of the factors which affect the gain, for which the technique employed is population inversion. You have to have an effective pumping mechanism which is going to remove more and more electrons from the lower level and keep sending them to the upper level, so that there is constantly a good enough number of electrons at the higher level for emission to keep taking place. So the minimum amount of population inversion that should happen so that gain is equal to loss is called the threshold inversion. So to quickly summarize laser action, we have the setup which consists of reflectors, the active medium and a pump. Pump is switched on, electrons go from the lower level to the higher level. Initially, a few electrons involved in spontaneous emission, giving out photons which travel randomly across the reflector. These photons trigger stimulated emission. The stimulated emission photons travel axially in a uniform direction across the reflector. When they hit a mirror, they get reflected back, so they keep traveling along the same path. These stimulated photons in turn continue to trigger more stimulated emission. Meanwhile, spontaneous emission is also happening. Spontaneously emitted photons might hit the reflector at haphazard angles and might be lost. Meanwhile, the pump is still running, so population inversion is also happening. So all the processes are going on together. So we say stable emission happens when the gain per pass, the number of new photons added during one trip through the resonator, is equal to the loss, the number of photons lost during the same trip. And loss, like I said, is not something which can be controlled externally. So to ensure stable laser action, it is necessary to make sure the gain is greater than equal to the loss. That is done by increasing the population inversion. So the minimum amount of population inversion that should be created so that the gain is equal to the loss and you have stable laser action is called threshold population inversion.